So that's an important thing to keep in mind also, is that when we talk about, for example, these last two, this one, which we refer to SLR4, which is the conditional mean assumption, and SLR5. SLR4 is clearly the most important thing for us. It'll be the reason we make most of our decisions that we make when it comes time to perform analysis, the so-called conditional mean assumption. There are a number of reasons why the conditional mean assumption would not be passed, or I should say, there are a number of reasons why the conditional mean assumption would not could not be assumed. One of the things that could cause us to violate the conditional mean assumption is that we are estimating linear relationships, but in fact, there are nonlinear relationships at play. So in other words, I write a linear regression, I assume a linear relationship, but let's say that in the population, the actual relationship is right? It's nonlinear. So in the presence of nonlinearities, we would violate the conditional mean assumption. Now, what does that mean? What would it mean to violate the conditional mean assumption? When the conditional mean assumption is violated, we can't trust our beta 1 estimate. We can't trust it. In fact, we refer to it as biased. We refer to it as biased. As I mentioned in the video that I posted, ordinary least squares is blue if OLS 1 through 3 hold and SLR 1 through 5 hold. 1 through 5 are the so-called Gauss-Markov assumptions. So those three properties of OLS, this is, don't ignore this right here. This should not say conditional mean assumption. It's like somewhat related to it, but it should, this is, I don't know why the typesetting program put that here. This should be here, just for the record. I changed it in the other slides, but this is clearly a different slides. I don't know why this is here. It's supposed to be down here. So just ignore this. In fact, let me just, no, not highlight it. That's kind of the opposite of what I want to do, you know? Let's do this. Okay, SLR4 is the conditional mean assumption, just so we're clear. Okay. So these are the three OLS assumptions, or properties rather, and then SLR1 through SLR5 are called the Gauss-Markov. Gauss being one of the most important statisticians of all time. There's all sorts of things named after Gauss, Gauss-Markov chains, Gauss-Markov assumptions. Very, very important statistician, both Gauss and Markov, obviously. The two most important for us Gauss-Markov assumptions are the last two. That's not to say that SLR 1 through 3 aren't important technically. It's just that SLR 1 through 3 is not typically as much of a problem. Like we make, you know, SLR 1, you know, that relies upon central limit theorem, law of large numbers. SLR 2 is just sort of represents the properties of sampling, which we discussed already this semester. SLR 3, that's just the statistical fact. You can't measure any sort of relationships if your X variable doesn't vary. What's interesting about that is that it doesn't actually matter how much X varies. Like X can be a binary variable, 1 or 0, and as long as it changes between 1 and 0 across your entities, you need some variance. And then these last two, these are the most important. And really, this is the most important. This is the conditional mean assumption. It's the most important thing. So again, what would cause us to violate the conditional mean assumption? Well, nonlinearities, okay? So let's pull up an example in Stata, and let me show you kind of what I mean by this. Okay, so I'm going to use a data set called BCU's wage. Maybe wage one. I'm going to try wage, but I might get an error here. No, I didn't. Okay, great. So, this is actually a different data set. Huh. Let me, I actually want to use the one that I'm used to. So BCU's wage one. There we go. That's the one. So this is a data set. I don't know what the year actually the data set is collected from, but this is what we refer to as a cross-sectional data set. You have individuals taken at a single point in time. That's cross-sectional. It's important to point out that when you have cross-sectional analysis, just think about where the variances would come from. Where are the calculated variances? They're going to be calculated relative to the people in the sample. So in this case, we have individuals. So there's individual one, individual two, individual three, individual four, so on and so forth. Individual one makes $3.10 an hour. That's an hourly wage. Maybe that tells you something about how old the sample is. But their wage is $3.10 an hour. Person one's education is they have 11 years of education. Person one's experience is they have 2 years of experience. Tenure means how long they've been at the same company. They have 0 years of experience. The person is white because their non-white is 0. The person is female. So you see that that's person one, right? And then person two, they have an hourly wage of $3.24. They have 12 years of education. They have 22 years of experience. That's experience is time spent working, and then tenure is time spent working at the same job. That's defined in the data set. That's not like common terminology. That's defined in this particular data set. But again, the person is white, and again, the person is female, and then this person's married, whereas the person one is not married. So so it's just, that's what we mean when we say cross section. I have individuals taken in a sequence. I have information with individuals, right? So there's no way that we can conduct any sort of annual effects. We couldn't look at time effects or anything with this sample. The only place the variances are taken from are across individuals, right? Just remember, the best linear estimator, okay, according to ordinary least squares, is the covariance in X and Y divided by the variance in X. So let's say that we were interested in the effect of education on wage. What does that mean? That means that the OLS estimator is simply going to be the covariance of education and wage divided by the variance in education. Well, how are the variances calculated in the sample? They're calculated across individuals. That's where the variances come from. In other types of data that we may have over time, you also get variances over time. We call that within variance. Here you get no within variance. I don't know what happens to anybody if they get additional years of education. I don't know what happens as experience goes up for individuals, right? I can try to measure the effect of experience, but I don't know what it means to actually get an additional year of experience for each individual. So that would have to be just an estimating margin effect. But the variances come from individuals here, just to kind of keep that in mind. That ends up being a very important point. So let's do a scatter and a line fit. I don't know why. All right. So this is a scatter of, oh, wait a minute. Sorry. That's not what I wanted to do. It's getting late on Thursday, you know. So only thing I find difficult about this class. Wage is the dependent variable here. There we go. Okay, so, okay, you look at this, right? Now, first off, the scatter looks a little weird to you, but it only looks weird to you because education is discrete. It's a non-continuous variable, right? We only have whole numbers, 1 year of education, 2 years of education. So that's why it looks like that. Now, when you look at this, well, you know, for me at least, this immediately throws off some concerns. First off, one of the things that is somewhat concerning is that according to this relationship, you know, according to this, one could actually estimate expected negative wages. You'll notice that the line crosses 0 before it hits the y-intercept. That would suggest that's a little bit of a concerning thing from a statistical perspective. That throws off. It's not super problematic, but it at least tells me there could be some problems. It's something to consider. What I care more about is what I can see are the spread of the residuals. And what I can see is that relative to the line that's been fit to these particular data, it doesn't seem like it really meets the relationship. Like, in other words, it might seem fine here. So like between 5 years and 10 years, this maybe looks okay. But then when you get past, especially 12 years, it looks like it goes exponential, right? It looks like all relative to the data, it looks like it is a little nonlinear. So if I'm worried about nonlinearity, then that would mean that I'm worried I'm potentially violating my conditional mean assumption. And I can't trust the estimation. The estimation is potentially biased. So how do I deal with this? Well, the first thing you can do is you can estimate a quadratic line. So instead of estimating a linear line, if you just change this to Q-fit, what that's going to do is it's going to estimate a quadratic. And if it estimates a quadratic, we should see the line. We should see kind of what it looks like if there is a nonlinearity. So let's do that. And so when you do this, what you notice is, like I said before, it looks fairly linear kind of in this 5 to 10 year period, but then you can see that the speed of the relationship picks up. So when we say that education and wage has a non-linear potential relationship, what we mean is that every year of education, the marginal change in wage grows, right? Because what does linear mean? Linear means that the marginal effect is constant. If you have a linear relationship, the amount that you expect a wage to rise relative to a year of education would be the same for someone who went from 9 to 10 years of education and someone who went from 22 to 23 years of education. If it was a linear relationship, right? That's a constant relationship. But with a nonlinear relationship, and specifically this one, it looks like the marginal effect of education grows with education, okay? This is also something that we found in a paper of mine that was published recently on the fiscal effects of natural disasters. We found nonlinear relationships, and that like small natural disasters have very, very small fiscal effects, and then large natural disasters, not only do they have large fiscal effects, but that they have exponentially larger fiscal effects, which is a pretty important result. It says that if disasters are getting more and more expensive, this is going to be highly problematic for states' fiscal conditions. All right. So now, what do we do about nonlinearities? Well, let's put that kind of aside for a moment and just we'll come back to that question. What do we do if we have nonlinearities? Let me go back to this part here and say that the main thing that we are typically worried about with respect to the conditional mean assumption. So I'm going to put some stars here. This is like the main thing we're worried about, and that is something called omitted variable bias. So another reason why we might violate our conditional mean assumption is if we have omitted variable bias. Now, what do we mean by omitted variable bias? What we mean is that we ran a regression, but with respect to a model that tries to explain the relationship between X on Y, there are other factors that should be included in that model in order for us to elicit causal measurements. Okay? Now, here's what I mean by that. So let's say for a moment that in addition to X causing Y, let's say that we have good evidence or perhaps good intuition that suggests that there is another variable Z, and Z affects both Y and X. So Z has some causal influence on Y, and Z also has some causal influence on X. This means that Z is a confounder of the relationship between X and Y. This is why the key to good statistical analysis and the key to good causal inference is having as much information as we can about the data generating process. And that information that we have about the data generating process comes from previous work in that particular field. It comes from our own intuition as researchers. Some of it comes from what some people would call common sense, perhaps. But it's important for us to understand how changes in X could potentially influence changes in Y, including those factors that would affect those underlying relationships. Because if you have something like Z that influences X and Z also influences Y, again, you can trust a simple linear regression, a univariate linear regression of Y on X. You would have omitted variable bias in that particular case. This one makes a little bit more of like intuitive sense why it's called that. But let's say, for example, that there's a variable M that we think X influences, and then M goes on to influence Y. That would be what we refer to as a mediator. It mediates the relationship between X and Y. If we don't have M in a linear regression of X and Y, that would also be omitted variables. And so we would have omitted variable bias. We would not trust a simple univariate regression of X on Y. We refer to this model building process, as it were, as model specification. You run a regression, you are going to specify a model. And when you specify a model, what you also do is you lay out in very clear terms the specific hypotheses that you are testing. Usually, we're interested in the influence of X on Y. We're not interested in the influence of Z on Y or the influence of M on Y. But we need to take their influence into account when we perform our statistics so that we can trust the estimation of the marginal effect of X on Y from a linear regression. In causal inference, this is the biggest issue, the number one issue, right? Half of my job as an academic is to write research. 85% of the struggle that we as researchers have in economics to get papers published is people not believing that we've dealt with omitted variable bias. Now, one of the things that you're going to realize is that how you specify your model is a decision of the researcher. It's up to you how you specify your model. Now, the idea is that you're going to specify your model in a way that I would refer to as best practices, right? If you ever take an accounting class, you know that you do this thing where you do accounting according to best practices, right? What are the tried and true ways that we know we can accomplish certain things? That's what we do when we run regressions. We rely upon best practices. What do we do? What have people done to deal with these statistical problems? We are going to do them because that's all we know to do. And once we've done them, we sort of reflect on how good we feel about how we specified our model and the results that we got. The difference between like old school statistics and causal inference is that in old school statistics, they try to take the choice completely away from the researcher. You just did the statistical thing, that's the reason why they didn't ever believe in causal inference. In causal inference, the idea is that if you can put together, specify a correct model, then you're able to elicit causal estimates. Then you're able to elicit causal effects. Now, does that mean it's easy to specify a model? Certainly not. But that's mostly what we end up thinking about. What are the things other than the thing I most care about that should be in my linear regression? That's what we mean by model specification. Now, going back to this point here,